My career by helping some brilliant biostatistician to come up with models, mainly in the genetic, especially in genome-wide association studies. So the first topic we would like to deal with is machine learning and deep neural networks. So deep learning, machine learning is a field of artificial intelligence that aims at providing the computers the ability to learn complex patterns without being explicitly programmed. It means that previously we write programs, still today we write programs like in C++, in different languages to talk to the machines, but this require to know all the path the program, the machine is going to follow. And when we learn in complex patterns, we don't have this ability. So the main purpose of machine learning is to program, to train these machines to do this, to achieve this ability without being programmed. If we compare it to this old statistical model, even though today we always use statistical models inside machine learning, the big difference is that in statistical learning we used to have a strong hypothesis on the distribution of the variable we use. For example, we can say that this variable is following a Poisson, a normal distribution, and so on and so forth. So these are very strong hypotheses we have when it comes to statistical models. The graph you're seeing below is just the ramifications of AI, of artificial intelligence, has a big field, and one of the building blocks of AI is first machine learning. We have also natural language processing. We have speech recognition. We have robotics and computer vision. So all what AI is. So just an example of machine learning algorithms. Random forest is one of the very famous machine learning algorithms, which is a combination of decision trees, if I may say so, and decision trees in which we add some randomness indeed. That's why it is named random forest. And we combine them as voters in order to say if to classify, for example, or to do even regression. Neural network is not algorithms. It's not algorithm. It's not a machine learning algorithm. We have also k-means, which is what we call a clustering algorithm. For example, if you have a bunch of people or a bunch of element or object, this kind of k-means algorithm can be used to group together objects that resemble each other's. So now let's have a focus on what really neural networks are, because neural networks can be considered as the main building block of AI, of deep learning at the moment. So what we have to bear in mind is that the neural network is just a mechanism. It's just an architecture that tries to mimic the human brains, and it can be defined as a sequence of layers. And each layer we have some input items that are called the neurons. So the first layer is called the input layer. It's where we push the data, and the data is going all the way to the last layer, which is the output layer. The in-between layers are what we call the hidden layers. So these hidden layers are really important because they are really designed with what we call activation functions, which aim at transforming the data they get from the previous layers in order to capture complex patterns by using some nonlinearity. So when the data is traveling from the input layer all the way to the last layer, we come up with an error. So this error is just a deviance, distance between what is really expected and what the algorithm come up with. So this is the first process where we push the data all the way to the hand, which is called the forward propagation. So once we come up with this error, we have to propagate this error all the way back to the first layer in order to readjust the weight. So indeed, each of the edge in between the neurons has some weight, and this weight needs to be adjusted to get the error the smallest possible. Excuse me. So this process is called the back propagation. Now let's deep dive a bit inside each of these concepts, because they are really important when it comes to handle deep learning algorithm and deep learning architecture. The first one is the forward propagation. The forward propagation, if we isolate one of the neurons, we consider that, okay, the data coming from the previous layer, here x1, x2, x0, xn are the input layers, and these input layers provide some data that will be weighted with this W you can see, and the role in this neuron is just to take the weighted average, and apply a nonlinearity function. This nonlinearity function is called the activation function, and it gives the output. So that we can find different nonlinearity functions, which are the activation functions, like the tanh, the ReLU, and the logit. It turns out that practically in practice, the ReLU turns out to be much more mathematically simple, because when we derive it, it gives a constant value, but also it is more computationally effective than the others. Now let's tackle with the back propagation. So the back propagation is about taking the error and propagating it back to the previous layer in order to adjust the weights. So here we have one weight, we have two neurons, we have the function error, the EW. So two steps are applied. So the first step is called the chain rule, where it is about to calculate the derivative of the error with respect to the weight and apply the rule chain. And this rule chain gives us a delta J. So this example gives only one delta J, but when it comes to a bigger neural network, we come up with several delta, which will be used in the update process. In the update process, here I'm just giving a very simple example coming from the gradient descent or stochastic gradient descent, where we update the weight by applying this product delta L x L minus 1 to what we call the learning rate. So indeed, the function error can be considered as a surface. It's often called the surface error, and this learning rate can be just considered as how fast we are going down to the minimum, to the value that minimize the error. So this is how we could take it. So just a few words about gradient descent. So this is the representation of the surface error. So we can take it as a model with two variables and one output. So two variables at the basement, and the output being the error. So what we're trying to do here is we applying different optimization methods. These different optimization methods are, for example, SGD, like stochastic gradient descent momentum, and so on and so forth. Each of these may be suitable for your model, but you have to figure out it, and you have to test and check your output, whether it's the faster to converge, or is it the best one that allows you to come up with better accuracy. Now, what is deep learning? This is the big question I would like to answer. So deep learning is definitely a field of AI, of artificial intelligence, and which is using sophisticated techniques to train neural networks with multiple, or I would say several layers. And it is using by using complex data without really, what is important is the fact it doesn't need to use manual extraction manual extraction of features. So years back, I would say, the researchers who are working, for example, in the field like computer vision, they used to extract the features from images before they process them in some other algorithm. Here with a deep learning method, you don't need to do that. So there is no sort of manual extraction of the features. So deep learning can be thought of as a part of representational learning, which is just the techniques that are applied to data to discover high-level abstractions, which is in machine learning techniques, which is overall in AI. So this graph is coming from a famous book by Jan Goodfellow and Joshua Benjo, which I really recommend. It's a really nice book, but it's a little bit mathematically intensive. So why does people even bother about deep learning? Why does it even matter? It turns out that there are some techniques that show up coming from the researchers. So the reason why people are talking more and more about deep learning is that techniques like new techniques helps, for example, to solve the problem of vanishing gradient and exploding gradients. For example, the vanishing gradient, if you take the example of vanishing gradient, it happens very often when we try to train a deep neural network. It means a neural network with several layers. The thing that happens is that the weights are becoming so small that they don't have any effect whatsoever on the readjustment, on the convergence of the error. So because they are very small, and when they are manipulated, they don't have enough effect to make the error smaller. So then the second technique is the representational learning. Techniques like recurrent, like CNN, convolutional neural network, they helps here to discover, for example, in this example of face recognition, where we can take an image or bunch of image and feed the network with these images. What we have indeed is at each level of layer, the network is going to learn high abstractions, higher and higher abstraction. It's what we call the representational learning. For example, at the first layer, it will be able to learn the texture. It will be able to learn the curves, the borders, and all this kind of low-level features. And then when we go to the next layer, you have more abstract layer, more high-level abstracted concepts. Like here, you can see eyes, nose, and etc. And the last layer, you can see a fully formed face, which is even a high abstraction layer before it goes to an output. So this is one of the techniques that also make deep learning much more relevant. So we also have this breakthrough in hardware performances. Today we're talking about the GPU. So the companies that are investing in deep learning, they all try to acquire GPU either on premises or in the cloud to have better performance. So the competition in deep learning algorithms are so intensive that we need this processing power provided by this sophisticated piece of hardware, which are the GPU, or even today with TPU, which is a hardware designed specifically for training deep models by Google. We have overwhelming data. Of course, the overwhelming data, data is becoming really overwhelming, and we have a lot of data, more and more, and we have very complex data coming from the sensors, the video, voice, speech, and all these data are really complex. And it turns out that the deep learning models that outperform the classical algorithms when the data is becoming much more important. So this is a few examples of deep learning architectures: convolutional neural network, deep belief network, autoencoders, recurrent neural network, and all these are often combined in complex problems. They can be used, for example, for computer vision. Convolutional neural networks are often used in computer vision. For example, autoencoders are often used in natural language speaking. For example, for coming up with what to vect, for example, is one of the example that can be used, and so on and so forth. All of these can be used isolatedly or combined in order to come up with architecture that solve the problems. When it comes to which tool to use, you will find a lot of tool to use for deep learning. Some are more related, more convenient for researchers. Some are more convenient to data scientists, to people who are taking the models into production. TensorFlow is really one of the rare the raw deep learning library that is able to provide both production level and research level without any modification whatsoever in between to productionize a model. So let's now jump to to TensorFlow. Let me check a bit if you have any questions here. Okay. Yeah. So the next step, so I'm going to tackle with TensorFlow 1.x. So TensorFlow is a open source machine learning tool that have been started by Google Brain team in late 2015. Indeed, it has been created for complex neural network, but it is really general enough to be used in much more variety of machine learning algorithm and or even computation systems. Any computation system can be applied to TensorFlow. TensorFlow is using what we call data flow graphs. So if you look at on the right-hand side, you will see this graph, and each edge of this graph represents a mathematical operation, and each node of this graph represents a mathematical operation, and each edge of this graph represents the tensors, the data that flows, as you can see in this animation, the data that flows from one node, one operation, to another operation to be fed with. And at the end, you will have a overall computational graph. So one of the characteristics of TensorFlow is it's highly scalable, and it can be used on pretty much all the devices, like the desktop, the mobile devices, and data centers equipped with CPU, GPU, and even TPU, the TensorFlow processing unit. And it is suitable. It is really suitable for researchers, data scientists, and developers. And the thing is, when you write your TensorFlow code on production at a research level, you don't need a lot of modification, or sometimes you don't need even modifications on the code to put it into production. This is one of the main building blocks of one of the main strengths, I would say, of TensorFlow. So when it comes to the architecture, at the very low level, we have the multiple hardware on which TensorFlow can run, and it can be CPU, GPU, etc. has a toolkit. And in the middle, we have this core component, the core execution system, which is all written in C++. And most of the people, even researchers, do not use it at this level. They use it at the higher level, which is a Python, some C++, but mainly Python. The API is also available with R, Go language, Haskell, and Java. But here in this presentation, we'll be using some example with Python. So now I'm going to go through different aspects, different features of the core API of TensorFlow. So the first aspect is what we call, the first feature I would like to talk about is the operations. The TensorFlow operations is, we can take it as abstract transformations applied to tensors in a computation graph. So it's on the abstract, but the implementation is what we call a kernel. So the kernel is a device-specific implementation. So in this table, you will see some example of computation of operation, like the multiplication in matrices, the matrix operation like the multiplication, and all operation related to matrices most often has a GPU implementation, which is much more sophisticated than the CPU because of the ability to make it parallel, to make this operation parallel when it comes to the matrices. But in different scenarios of building your model, you may be using one implementation rather than the other because of the implementation, because of the efficiency. One other aspect of TensorFlow Core is what we call the TensorFlow variable. So the TensorFlow variable is what we can consider as a data structure. Indeed, it is an in-memory buffer containing tensors, and it represents your parameters of the model. So if you have any model, for example, that predict, that classify is whether someone is a fraudster or not, the parameter of this model is represented by a variable. So, but these variables are really different from the normal tensors because they have the ability to survive beyond the computational iteration. That's why this variable, you will see it in the example we will go through, this variable can be used in gradient descent method to optimize after a few iterations. So another characteristic of the variable is that it can be serialized and that can be persisted on the disk, or even that can be loaded back, that can be deserialized in order to be used for serving, for example. One thing that is really important and to bear in mind when it comes to using TensorFlow Core API is when you're using variable, you need, when you execute your graph, you need to initialize them. I am giving two examples of how to create and how to initialize the variable here. So TensorFlow variable has the variable TF variable, and TF variable has a first parameter, which is an initializer. So this initializer, you will find in the Core API different initializer. Here I'm just initializing it with a normal distribution, which is truncated. I think the two standard deviation before and after 0 are being just removed from the initializer, and all the others are just generated randomly and have initialized of this variable, and there is also the name given to this variable just for visualization purposes. Initialization, we need to initialize it in the session. We'll come back to the notion of session lately. The method global variable initializer is a main method to initialize all the variable inside your model. So another concept that is really important for TensorFlow Core is the TensorFlow placeholder and the feed dictionary that often goes together. So the placeholder can be thought of like the mechanism that allows you to feed data inside your model. So here I'm giving the example of input A, input B, like variables and their types. It can be a more complex variable. It can be a tensor. Most of the time is a tensor. And of course, by the way, pretty much everything in TensorFlow is a tensor. Pretty much everything. And here output can be considered as a model. So the model is about just taking two output and multiplying them together. So we multiply them. So in TensorFlow, nothing is done unless you run the model. So if the model is output, you need to run it in a session. So the session is indeed the containant, the logical containant that is going to run your model. So we're creating in this concept initializer context initializer, this Python concept initializer, we have this session.run method that will run the output, which is considered as our model, and the feed dict is going to be the structure, the dictionary here that will be used to feed the data inside the output and to get the result. And at the very end, we have this print result that will just print the result. So two things here: placeholders are inputs, and the feed dict is used to feed the data inside the output, which is the model, by using the run method. And of course, here you can see that we're not using any variable. That's why we don't have any initialization. So as I told you, when it comes to running, when it comes to building a TensorFlow program, there are two steps. The first step is assembling in a lazy way a graph. So the graph is about declaring the inputs, which are the placeholders, declaring the variables, and creating the model, which is a combination. This can be different operation that links together the input and different variable you put inside. And it can also include, and often includes, optimization methods. And at the very end, you use a session to run everything. So it's really important to understand that. So here, let me present just what sessions are. The sessions are what the logical containers that allows you to run your TensorFlow graph when you are using the Core API. So it has the responsibility to build the initial graph, which is the computational graph, the first computational graph that is not being updated, and to initialize the variable, as we've seen, and run with the run method inside the context, inside the session. So these are the three things a TensorFlow session is doing. But when you are in a interactive session or Jupyter Notebook, it turns out to be handy to use what we call interactive sessions. And TensorFlow has such an object that makes it easy to use to do the computation without creating any session. So for example, here we are creating in this snippet, we are creating the C variable, which is just the multiplication of x and pi. And then this C is used, I mean, the eval method is used on C just to find the result. And you don't need any session object here. And at the end, of course, the session object is closed because it's interactive. So the mechanism is built such that you will not be, it's not needed for you to wrap the execution inside a session block. So a new feature inside TensorFlow is what we call the eager execution. It starts from TensorFlow 1.7. In TensorFlow 1.7, we have this eager mechanism, this eager execution. This eager execution is just an intuitive, is really an intuitive interface, because it lets you use the same components, the same TensorFlow components, like any common Python data structure. It makes it handy, and then it makes it handy because you have the ability to debug your code by setting some breakpoints and going through the assigned variable and use the natural control flows, like the loops you find inside Python. It really makes it really easy. You don't need any session to create at the very beginning, or when you're running your model, when you are in eager execution. So I really recommend it when you are building your model and you are doing some testing on some experimentation. Okay, now I would like to wrap all this concept together in one working example. The example is just an algorithm, an ancient algorithm that is called the Babylonian algorithm, and which is this sequence UN equals this expression, and we know that for a very large n, this sequence is going to converge to the square root of x here inside the expression. So the expression, I mean, how to write it in TensorFlow, we have two components: the built computational graph, where we import the TensorFlow object. I'm importing NumPy here. I'm setting the first epsilon. So because here, what we're trying to do is to check the convergence of a sequence of numbers. So epsilon is very important. It's sort of the tolerance between u subscript n and u subscript n minus 1. If this distance is smaller than epsilon, I will just stop the process. So the value here is, I'm using cas x, and cas x is used, is being used inside. The value is a constant, so I'm using TensorFlow.const inside a cast. That cast it has a float number, because I just would like to have a float 32 number. So I'm defining the first value of the session, the previous value of the session, un minus 1, which is a variable. And then I'm defining the next value of the session, which is the assignment of un minus 1 with the expression we defined before. So 0.5 is a half multiplied by this expression. So we need now to run this model, because this model needs to be run inside the session. In a typical model written using a TensorFlow API, Core API, we need to run everything inside the session. So we use the session.run, and we initialize it first, and then we have this while loop to compute the value. So I'm going to switch now to a notebook, and this notebook, famous tool of Google, Colab, and Colab is just a sort of a collaborative environment where you have not, you can Google document, and you can share it with people you are working with. So here I'm implementing the Babylonian algorithm, the Babylonian algorithms, where we start here with this epsilon. So by the way, before I did what I did here in the first line, I don't know if you are seeing what I'm writing. Okay, let me go back to the Babylonian algorithm. The Babylonian algorithm is first importing everything, importing TensorFlow and NumPy. I think it was not running now. I think the kernel is now running. So Colab is really nice when you start and you don't want to have a lot of setups on your machine. So you can just spin up a VM. I think behind the scenes, VM is spun up, and you can use TensorFlow version. You can use either Python 2 or 3. So here I used to just print the version just to make sure. So we have the last version of TensorFlow. So the Babylonian, so we have some markdown text. You can write to make your text much more readable for people you are working with, Okay, so the epsilon, I'm running the epsilon has a constant. So I'm running here, I'm building the model here. So x is casting this value. So 1, 2, 3, 4, 5 has a value. So I just change a little bit the type, but it's not a big deal. So the u subscript n minus 1 and the un. So let's run it. But up until now, nothing is running indeed, until we reach this session block. So this session block is doing two things. So the first thing is doing the initialization, and the second thing is doing the computation. So if you run this, you will see that after 1, 2, 3, 4, 5, 6 iteration, we come up with the real value, which is the square root of this value. 1, 2, 3, 4, 5. I think you can double check with your calculator, and you will find that this algorithm converges well, and we have the square root of this value. Okay, I'm going back to the slides. Let me see. Where is it again? Okay. So this was the Babylonian algorithms. So one of the building blocks, really important building blocks of TensorFlow in general, is this TensorBoard. It turns out that when you building a deep learning model, chances are that the deep learning model can be very complex, and deep learning models are notoriously hard to debug and optimize. We all know that. And TensorFlow board is coming to the rescue by making it easier, and it provides a web interface for you to go through your code and understand the graph, understand the value. And often what you need to get this TensorBoard is just first to decorate your TensorFlow code by this naming convention, by this name scope function or method. And I'm going to show you a demo of that, which is a linear function, a linear regression. So a linear regression I have already implemented here in this Colab. Don't worry, at the very end, I'm going to share all these labs. So the first thing I'm doing here, of course, is running this importing TensorFlow. NumPy often imported, but pretty much all the feature of NumPy can be found inside TensorFlow. So I just use it. I just do it most of the time. The main reason why I do it is just because here I'm generating some fake value, some fake. So I'm generating the X data and the Y. So here, let's generate it. It's done. So here, this I'm commenting out this line because I don't need it. This Colab has a built-in matplotlib inline. So you just run your model, and you will find you just run your code, your display code, and you will have your nice graph like here. Here, what we have is what we generated. So what we would like to do is create a linear model that will fit this this cloud of points, which are just this equation we wrote here so far. So this equation, we wrote it, and we put some noise around. So we can put more noise here to make it much more even wider. Let me try to. Yeah, it's more noisy. So this more noise indeed. So what we're doing here is, okay, we're using this name scope has a context manager inside Python, and we wrap it inside the creation of the model. So the model has two components, W, which is the weight. So we're using the variable truncated. Let me make it bigger. Variable, and we give it the name W. And here we have this variable B, which is the bias indeed. It is one only. I mean, it is one size. The dimension is 1. And here the model is Y of which is just taking the weight multiplied it by X data plus the bias, which is typically a linear model. And what we're doing here, we're creating the error function. So the error function is this loss function. We reduce by reduce mean. We use the mean square error, and then we just pick a gradient descent optimizer with the learning rate 0.1. So the trainer is just optimizing this loss function. We define here the number of iteration, and here these are some syntactic sugar we use to gather all the information about this variable you create and the model we created. Okay, I think here to be able to show you the dashboard, the TensorFlow, the TensorFlow dashboard, the TensorBoard indeed, I need to run it locally. because I don't have access to, let me check. Okay. So what happens here when I run the model is pretty much the same model as I have in Colab, is exactly the same. At each iteration, we have this blue line that is going to try to be fitted inside, to be fitted in the model. So it is trying to fit these points, these red points. If you can see that at every step, the model is getting better, better, and better up until the end, where we have pretty much a perfect fit. So what do we need really to get the information of what's going on behind? We need to run TensorBoard log here, and we need to give the summary dictionary. Okay, indeed, if you go back here, we are populating all the statistics of this computation inside this summary folder. That's why here we provide to TensorBoard this log folder. So we have now just to jump in our console to log 6006 to the TensorBoard. And here the model is quite simple. And inside what we have is this training and this model. So if you remember what we did, if you go to the linear model, what we build here is this block of model. That's exactly what we find here. So we have this W and we have this B. So this W is one of the components of the model that is multiplied by this by the data. And then we add this bias indeed. And in the trainer, what we have, we just to have this block that represents the optimal. We have a much more meaningful, much more complete, I would say, graph. So here, the idea is to have a better view of your model. Let me check if you have more things here. The color. Okay, I think I will come back to a more meaningful example. Let me close this one. I'm going back to my presentation. So that was the linear model. So here, this is, for example, what you see is the model with the W and the B being added. So with the multiplication of the Y with the W added to B added to this multiplication. That's what we have here. Now, okay, I would like to show you a bit about the model we can build and show you more meaningful. Maybe I will jump this one. I will try to build a more complex model just to show you how it can be done in TensorFlow. So it's going to be the deep. Let me check. Okay, I think this is this one. This one is using really the core API of TensorFlow. It's quite high level. The idea is to show you what we get in high-level API and what we can get in a much more easy way, which is the high-level API. So here we are loading TensorFlow and we are loading the MNIST data. The MNIST data is handwritten digits, very famous. I think have been created by the team of Yann Lequin. And what we have here, okay, this is just a working directory. So this is really the function I'm using just to gather all the information about the variable or that are being used inside the model I'm creating. Don't bother about what is inside really. Where here, this is a function I created just to create some layers by providing the input dimension, the output dimension, the name, and whether it is softmax or not, and whether I am applying a dropout or not. So this is how I created the model. This is a summary. This is for TensorFlow board. This is for variable. And every time I'm creating the variable I'm creating some summary about this variable and putting it inside this variable summaries, which is the function I defined before. So here I'm applying a ReLU, had an activation function, and here I'm saying, okay, I'm just checking if it is softmax or not. So, and if it is, I'm applying dropout or not, and what is the percentage of dropout. So here is how I really build the model. So the model I'm building is this model where we have the first layer, which is the output. What we do is we're taking the image, what we have here. This is handwritten digits, and each of the pictures is one handwritten digit. And what we do here is we flatten in the first layer, and we create some hidden layers. So the first hidden layer with 200 neurons, the second with 100, and so on and so forth, up to the hand, which is the output, which will classify which of these digits this picture is. So if you go back to the to our code in Python, you will see the first layer, second, etc. So I'm using this function I'm creating, and of course I'll start by creating the input files. So the input files for the X for the layer. So you can see that this is the 20 by 28 by 28 picture. I'm flattening it by multiplying the shape, the dimensions, so that we have one single shape. And here, this is the output where we use to compare the output of the network. So the first layer is here. This is the input. The first layer, the second layer, the third layer, and the last one is the fully connected layer with some dropout. Dropout is just a normalization mechanism that allows you to remove what we call some biases due to the fact that we're overlearning the model, which is I forget the name, but yeah, you get the picture. So the loss function here, what we do here is we're creating the loss function, the cross entropy loss. We use the mean square error. It's kind of mean square error, but it's not really, because we are using a softmax cross entropy with logit. We sort of just create a normalized probabilistic vector where each of the columns represent a probability, and it sums up to 1. That's what we're creating here. And here we're creating the trainer. So the trainer is just the optimizer with this learning rate, and we providing to minimize this loss entropy. Okay, this is what we're doing. And here we use the accuracy operation where we, by our own, we create the operation that allows us to have the accuracy of the model. So here the accuracy is the mean square error of whether we have the correct answer or not. So the correct answer is testing whether the predicted value and the expected value are the same. And the accuracy by definition is just the mean. And we just putting it in the resume for TensorFlow board. Building, now here we are running the model. So we are running the model by batch. So we're running the model. The first thing, as I told you, was the initialization, and then we merge everything related to TensorBoard. And here we have different iterations. So this is what we call the epochs. So the epochs, one epoch is when the algorithms is processing the whole data. So if you run everything, let me run these models. Oh, sorry. We have some error. Well, let me. Oh, what is this? The summary. Oh, yeah. Sorry, I'm right. I'm running. I'm coming. I'm coming across some errors, I think. Yeah, I don't have time to investigate it. Let me rerun it. Let me rerun the, yeah, and rather than doing it here, let me do it on my console. I'm running everything again. Okay, yeah. Not this one really. Yeah, it's more this one, MNIST. Okay, yeah. Well, yeah, I think it has to do with the kernel, indeed. Okay. Let me check. I don't know if you're following me, but it sometimes happens. Where's the kernel? Okay, yeah, now it's happened. So sometimes it happens because of the kernel going crazy. So what we have here indeed is the algorithm trying to optimize and get a better accuracy at every single step. That's what we have here. And as you see, the algorithm is getting better and better indeed. Okay, I think there are a lot to cover here. Let me go back to my presentation. And now I would like to just present the high-level API of TensorFlow. So the high-level API is really the way to go when you would like to use TensorFlow as a beginner. So as a beginner, I suggest to use this high-level API. So the main building blocks of the high-level API are the dataset. So the dataset is a mechanism to load the data and feed your data to inside your model, but in a more intuitive, in a more easy way. The second are the building blocks are the layers you can use. For example, you've seen that I've created create layer method that allowed me to create a more complex sequence of layers. Here, it is already provided in the last version of TensorFlow, since I think 1.2 even. And you have other really interesting layer of abstraction on top of the core API of TensorFlow, like Keras and the Estimator API. So the first one I would like to present here is the Keras API. So the Keras is a deep learning API with syntactic sugars expression that really makes it easy and simple to use TensorFlow. Keras is really integrated now with TensorFlow. Before it was an independent, still existing right now, indeed, and you can use it. And it has the same level of abstraction, has layers API and the Estimator API. So here, this is a simple example of what we had before, where you just create a model with one line, a sequence model. This is a type of model. You can have a different kind of model, but this one just means that we are creating a sequence of layers, so sequential model, and we end up adding each layer. Here, the first layer has 28 multiplied by 28, so 684 neurons that feeds this model has an input, and the output size is 256. And then we add another layer, which is the 10 neurons layer with a softmax activation function. So, and then we use the compile method with define the loss function. Here we define it just like a string. There are a bunch of the strings loss function you can find in the documentation. We define the optimizer, as I told you. It can be an ADA, has the ADA delta. It can be stochastic gradient descent, and here we can just give the metric, which is the accuracy model. And we use the method fit to fit the model. And lately, what we have here is a loss accuracy computation by using evaluate to evaluate the model on the test set. And then we can go about using it in production by using, for example, prediction. So it really makes it very, very easy. I'm going to show you an even more complex model built with Keras. Let's take back this model, this TensorFlow model with this deep neural network, but this time we're using TensorFlow Keras TensorFlow to build it. Okay, let me make it bigger. I think my fan is going crazy because of what I'm running here. Let me stop it. Yeah. Okay, it's getting better. Well, here, what we have here, of course, the first thing I'm running TensorFlow, loading TensorFlow, first step. So the second thing is I'm loading the Keras, using the Keras dataset module, I'm loading the MNIST data. Okay, it's downloading it, okay, from Amazon Bucket. Okay, Amazon S3. Okay, here, what I'm doing here, I'm reshaping, because if you go back to our model, this is flattened. So it says a 28 by 28 matrix, a 28 by 28 picture. But here we need to flatten it. That's what I'm doing for both the test and the trained. And also I'm making the output, the label, categorical. That's what I'm doing here. And now we are rebuilding the same model we built in this notebook, but here it was in a much more complex way by using this complex model. You don't need anymore to write this kind of model because it comes out of the box. It makes it much more easy for you to build this kind of model, Keras model. So Keras has this layer and dense layer where you define the activation, you define the input if it is the first layer, and then you define the activation, the output size, and so on and so forth. You can have even more sophisticated like the flatten, the dropout normalization, and at the end, this last one is a 10 output of which are the 10 digits, and the activation are softmax. And of course, you go ahead by defining the loss function, the optimizer, the accuracy, the metrics that should be used. So let's run this one. Okay, the model is built, and yeah, you can run the fit commented. Okay, I received a comment. Sorry. Okay, I'm going back to my slides. Okay, here, am I receiving a message? Oh, Ryan. Okay, I think Ryan is starting her session or not. Okay, let me just try to finish this one. Okay. Well, let me close this. Okay, let's go back to my explanations. Okay. Well, the deep learning. Okay. Oh, again, we have the same problem here, I think. Invalid shape. Oh. Okay, I think I have to restart. Sometimes it happens, indeed. I'm going to rerun everything here. Oh, okay, it's not this one, indeed. Okay, this was the Keras one, indeed. Okay, this model, I'm feeding this model here. So here it is trying to fit the model, indeed. So you figure out that, okay, what you wrote before in the previous notebook is much more complex than this simple piece of code nicely written in Keras that helps you make the code much easier to read, although behind the scene is much more complex. The model is much more complex. Okay, this is going to run and come up with a model, and then that can be used to, so here we have 100 epochs that will be used to fit the model. So this was just check. So prediction and the actual value are the same. Not for all the examples, of course, obviously. Let me go back to deep learning. I think I'm receiving some messages. Okay, let me share back my share. Okay, here I'm going back to the presentation of Keras. So that was Keras, indeed. Now I'm going to present very rapidly the TensorFlow API, the high-level API, starting from the dataset. So the dataset is now a high-level API. So if you've used TensorFlow in the past, it turns out that it has been really very difficult to use to load the data. There was absolutely very complex. Now the newer API allows you to load the data pretty much like what you have in other libraries like scikit-learn. So you can load it from different structures like text line data sets. It can be a text. It can be some other structure like the TF record data set, which is protobuf and fixed length for record data sets and so on and so forth. You come up with ready an object that can be manipulated, and I'm going to show you how. I'm going to show you later how it is manipulated. So the second thing is the Estimator API. The Estimator API now you don't need to re-implement all the classical and common methods like the linear classifier, which is here just the linear classifier here, or the linear regressor. You don't need any more to re-implement all these things, because all these are really known and it's really boilerplate to implement all these things. So there is what we call pre-made estimator, and that can be used right off the box inside your algorithms. And if really you need to implement something really customized, there is what we call the custom estimator. So to gather everything, to put together everything, we have on one part we have the dataset API. So the dataset API will help you come up with a test set, your train set, your validation set. And you have different operations, like a map. Map allows you to apply some operations. You can have batching, which will slice your data set into batches and feed it into your mechanism. We have padding, repeating, and shuffling. All the name are speaking from their name. And they all can be used inside a function that is called the input function. So the input function is the only function you need to implement if you want to use a pre-made estimator. So any pre-made estimator, any estimator inside TensorFlow is implementing a model underscore fn, the model function. And the model function has mainly 3 building blocks: the train, the evaluate, and the predict. So now let me jump to an example just to show you how we can leverage this these estimators, this estimate API. Eager, let me see. I should have one example here using. Okay, let me show you an estimate API here. I'm going back to my very high-level API. Okay, here I'm using here the example of iris data. I'm switching to my local, so I don't have it in the Colab. So here, okay, I'm loading the data. I'm loading, the libraries. Okay, this is just loading the data. But here, what I would like to show you is more how to build the estimator. So the first thing is what we call the features. So we have the iris data with this sepal, petal length, and width that will be the feature variable. So here, what we need is to implement this this input function. I call it iris input function, but basically we'll find the same thing. We have a parser that will decode the line. So it's the features, the data is coming from a CSV file, and we export dictionaries label. That's what we have here. And we have here the ability to use this parse inside this function. And that's what we're doing here. We're loading the CSV file. We're shuffling it if it is in training mode. So this is the training mode indeed. And here, what we're doing here, we're doing the shuffle if it is, and we're repeating. This is the number of time. This is the number of epochs. So we're repeating the number of time the data should be fed inside the algorithm, inside the Estimate API. And here, this is the batch size we define for this API. And then here, we create the iterator. And what we do here from the iterator, we just return the batch features and label. This is what it takes to build an input file. So it's pretty much the same pattern you will find, even for an image and so on and so forth. So image, it can be a bit different in the loading, but pretty much the same is the same pattern you will reproduce. So this is the function. So here I'm using okay, just showing the result inside because here I'm not in the eager execution, because on my local I don't have I have only the version 1.6. And here I'm using an already available model, which is this DNN deep neural network classifier. So we have these features where we go through all the features here and we make them numerical. Indeed, TensorFlow has this feature column with a numerical column feature. You will find different kind of transformation for your features, and you can go through all of your features and do the required transformation for your model to be used. So this is the classifier we define. Yeah, so we define the feature column, we define the hidden. So here, this deep neural network has 2 layers. The first layer has 10 neurons, the second has 10, and we have 3 classes, which are the species of iris. And this is the model, where the model is stored after being computed. And here, what I'm creating here, a lambda function. This is an inline function that will give you the input function indeed. So this is for the trainings where we define all these things, the epochs, the batch, and the file path in this case. Okay, this is loading everything. Now comes the test input function. For the test, we do this pretty much the same thing, but here we just eval. The mode is not trained, so we don't need the shuffle, which is an additional operation. And here we retrieve the accuracy and display it. So we have pretty very good accuracy of the model when we run it, and so without any decoration whatsoever on the code, you have the ability to have to run your TensorFlow mode. Sorry for this. Your TensorFlow board, and come up with a board you can explore without explicitly telling it to TensorFlow in the code. So the Estimator API has already a built-in mechanism to get all the variable around and come up with a TensorBoard. That's what we have here. We can use it to predict, okay, this is the probabilities we have, and so on and so forth. Okay, let me go back to the presentation. So this is it for TensorFlow high-level API. So in the high-level API, we've seen 3 things. The first thing was Keras, which makes TensorFlow easy to use, I would say. And for any developer, any data scientist, anyone who is new to deep learning, it is really a way to go. If you are starting to use TensorFlow or deep learning, I deeply think that Keras is the way to go. And then you can go more in the other aspect of the high-level API, like the Dataset API, the Estimator API, and so on and so forth. Now, this is the last thing I'm going to mention to go through, which is data science on Google Cloud. So Google Cloud is really a very sophisticated bench of tools. This is an ecosystem. So by using Google Cloud, you will benefit from the in-house humongous platform Google is using inside its doors to run amazing tools like Gmail, Google Photo, Maps, etc. So Google using pretty much the same things indeed. So here, what do we have? There are 2 ways to do machine learning in GCP. So the first way is, I would say, the easy way. The easy way is to use the pre-trained model, like the Cloud Vision API, the Speech API, the Job API, the Cloud Translation API. And all these tools are just a bunch of API. You can just use a JavaScript and to run this API and apply your data and use it right in your application. There is what I call the hard way. The hard way is leveraging all the other ecosystem of data proc to process the data, Cloud ML to build a model with TensorFlow, and Kubernetes, which is an orchestration system for containers like Docker or Rocket. So when it comes to ML, it's not only about writing TensorFlow code. It's deeper than that. There are more work to do than that. There is the data collection, the data manipulation, and the feature engineering, the logging, and make sure that you serve all this in a scalable way, and you monitor all these servers running. So you need really to master this, and building the model is just one very small building blocks of the whole ecosystem you need to operationalize your machine learning solution. So here I'm showing you just an example of one of the projects I've been working on lately, where we have this on GCP, where we have this training layer, and we have some bunch of images on which we do some processing, push it in a BigQuery, and we also leverage the data inside inside Google Cloud Storage, and build the model, put the model inside a repository and expose it as a REST API and to be consumed by a client. It can be a it can be a mobile app, it can be a desktop app, and so on and so forth. So this is another example I built a little while ago by leveraging the cloud, the triggering mechanism inside the cloud storage, where when some raw data are pushed inside cloud storage, a cloud function is still triggered, and it will call a pre-trained model inside a model I already trained inside Cloud ML, and push the data inside BigQuery. So this was the mechanism I use in a very recent project I have been working on. So what does it take to train your model inside GCP? So there is a need of packaging your algorithm. So I'm going to show you. So what you can see here is a bench of Python files that have been written so that you can package your model and push it to Google Cloud in order to serve it in your ecosystem. So I'm going to switch to this example. I'm not sure you were seeing very well. I don't know if you were seeing very well what I'm showing. So I am in on VS Code, Visual Studio Code. So VS Code, in this project, we have this Python environment. You can see here is a Python 2.7. So the trainer is what I really built. So the main object, then the main file is this task file where we really defined the model. We have this input where we define how we do the transformation and so on and so forth. We have the metadata where we define how we run it. Indeed, the featureizer is how we do the feature engineering. And this is a predefined way of how you really have to package your TensorFlow project to be able to run it. So I have created a folder here that let me push the data inside. So there are two ways. The first thing, it is recommended to, I'm using this G-Cloud function and using this ML engine service to deploy it locally. So I'm just running locally to make sure that everything is running. That's always what you need to do when it's to building, pushing it in GCP, Cloud ML. And here, so I created this project just for the Hajj Hackathon, just to show you an example of how we can use it in Google Cloud. So these are different parameters you can use. So like you have to create a bucket, of course, a cloud storage bucket, and you put the data. That's what I did here. So here, this is the runtime 1.8. And all this information are needed to run your model in GCP. So, and here, I'm going to run it and show you. Just paste it here. When I paste it, oh, I need to run everything indeed. Well, now normally, Google Cloud is submitting a job. Yeah, so the job is submitted. It's submitted, and if you go to your, oh, I think I have some problem here. What happens? Let me make it smaller. I'm not sure I copied everything. Oh. Let me check if I am in the okay. I think I made some compare it. Oh, I have some. Okay, yeah, I think I have some security issues in my. But yeah, normally it should definitely work. Let me try the local one indeed. I think I did some modification on my GCP. But normally here, if you don't have, oh yeah, I think the same problem because, oh yeah, okay. Oh yeah, the thing is here, I need to source my Python in activate, of course, and then I can just run it locally. I need to activate. Yeah, now it's running locally. It's for some reason there is some issue in my Google account, Google console, GCP console. I will need to fix very soon. So now you get it. This is just an overview of how you can do data science in GCP. I think that's it for me. I don't know if you have questions. Obviously, I will be sharing all this content in my GitHub, and I will give it to you guys. If you don't have any question, thank you for being here. I think there was a lot of to cover, and I did my best to try to cover everything. I think it was quite fast, but yeah. The thing is, it was covered. It was just a chance for me to give the most I could give you. If you have any question, just let me know. Okay, thank you, guys. I think I'm going to stop the broadcast and call it a day. Thank you for having been here. Thank you very much.